Okay, lastly, I do this for undergrad, but I think it's vitally important that we at least witness the benefits of a cache system. So we're going to do hopefully a very simple problem. Y'all are familiar, at least with passing, with, what's it called? Matrix multiplication?
Yeah.
Yeah. So we're going to do, matrix multiplication?
I don't recognize that term.
So if you have two matrices and you want to multiply them.
Right.
So let me,
Vectors.
yeah, well, a matrix is a two-dimensional vector. So let's go ahead and create, well, let's make a smaller one right now.
Matrix, I heard something else.
Oh, what'd you,
I don't know.
matrix, okay. So we'll have A, they'll be width by width, so we're lazy today. B and C. And the idea is that we're going to go ahead and try and multiply these two things. Hang on. Turn 0. So first off, we want to, well, we got to include standard lib. All right. So we want to first populate A, B, and C. So for int I equals 0, I is less than width, I equals plus. For int j equals 0, j is less than width, j equals plus. And we'll go ahead and, was it a sub I sub j equals, we're going to do rand. What's that? You want me to seed it? Okay, fine. What do you want me to seed it with?
11D.
11D. There we go. I'm not going to put a D in there. Alright, so give something for A, give something for B, and well, we want C to start off at 0 because C is going to have the final answer. Whoops. And then just to make sure things are actually being printed off correctly, let's go ahead and do a quick little printf, %f, A sub I sub j, comma B sub I sub j. Alright, let's go ahead and create a new little terminal, gcc, mm.c, we'll call it mm. Hey, compiled. Alright, good, we're getting some random numbers. Looks like they're between 0 and 1, which was the intent. Perfect. Okay, and we don't want to print all of them out, that would take too long, so let's just do, we're going to only do one of them. We'll do the first 10 of, let's do the first 10 of A. There we go. Okay, great. So we want to do matrix multiplication. All right, so let's go ahead and make a little function for that. Matrix multiply. All right, so I probably don't remember how matrix multiplication works.
Just do it slot by slot.
Quick, go ahead and explain it to everyone, Matt, while we still have time.
Multiply the slotty slot by the slotty slot.
I'm sure everyone at home just got that.
I'm sure they did too.
Who do you call it a slotty slot?
I don't know.
The matrix.
All right, so this is matrix multiplication.
Yeah.
Yeah? What you're doing is for every cell that's in C, you're going to go along the, whoops.
Yeah.
Let me fix that real quick. Oh, much better. You're going to go along, what's that? The columns of A and then multiplied by the rows of that B. So you're kind of going, like one's going up and down, the other one's going down the row, and you're multiplying each of those elements and then summing them together and putting them inside of C. That's matrix multiplication. Right, Matt?
Yep.
All right. Let's go ahead and print off C just to make sure it's actually giving me something. You know what I probably should also do? Call the function. Right? I mean, sure. Hey, there it is. Okay. Let's go and turn on optimizations. Well, hold on. Before we do that, let's let's set up timing, because we haven't done that either. Right, Matt?
Yeah. I don't know, man. It's almost like there's something due.
So we'll create a start and an end. So we'll have start equals clock. And what this does, this is the C way of calculating the number of clock cycles that goes by. So we get the number of clock cycles before we call the matrix multiply, get the number afterwards. It's not perfect, but it'll work.
You want to subtract them too?
Yeah, we're going to want to subtract the two, so let's go ahead and create a double called diff. Diff equals end minus start. And then we'll go ahead and printf took %f seconds backslash n. What?
Yeah.
Clock per sec.
Yeah, because I was about to say, wouldn't that give you just the clocks?
Yeah, so you got it divided by clocks per second. And then that should give you the final answer. So let's go ahead and run it. Took 0.161 seconds. Let's go ahead and turn on optimizations real fast. 0.03. Hey, look, the compiler did a lot, didn't it? Okay. Well, let's go ahead and bump this up to 9 real fast. 477 seconds. Okay. Let's go ahead and take this. Let's record that real quick. And let's see how much it takes for... Oh, are you familiar with this operation?
I was going to ask you about that. That looks like a shift operation.
Yeah, so 1 upshifted by 9, aka 2 to the 9th. 512.
Okay.
1 upshifted by 10, 2 to the 10th, 1024. It's just, for me, I've been doing it's easier to read it this way.
So let's go with that.
Okay. We'll do it for this one. Now, come on, got some good background music? Nothing? .05, which makes sense because matrix multiplication is an n-cubed operation. So going from doubling the input, going from 0.4 seconds to 14.05, that makes sense. So let's go ahead and record that real fast. All right. So the question is, or the question I have is, how could we utilize the cache better here? Well, if you look at it down here, the problem is when you grab these values from A and B, they are not in general in the cache because you're going along, you're jumping down the columns or you're jumping down the rows, jumping across the columns. So you're not really utilizing the cache. In other words, if you look at this, there are many cache misses inside this operation. So what we want to do is rearrange the code so that it actually fits inside, more of these references fit inside the code. And the way you do that for matrix multiplication, and instead of iterating through the whole 2 matrices whenever you do a multiplication, you only do certain small blocks at a time. So you can do one small block that fits all in cache, another small block that fits all in cache, and then move maybe the second block over but keep the old one so that you are only working on certain blocks. Do you see what I'm trying to...
Yeah, I think there's a
understand what you're
picture for
saying,
that.
because you can't fit the full matrices in the cache.
Yeah, okay. And this is called matrix multiply blocking. And we're going to go, before we call it, let's go ahead and put our width back down because we want to make sure our blocking code works fine. And so the answers we have 62.78. All right, great. So let's go ahead and do matrix multiply blocking. And let's just copy pasta this code. And we'll get rid of that matrix multiply blocking. Great, let's go ahead and compile it and make sure it works. All right, we're still getting the same answer. That's good because it's the same piece of code. All right, so how do we do this? Well, we first need to find some type of step or some type of block. So I'm going to call it define step, and I'll make it 1 upshifted by 3 for right now.
So 8.
Yeah, 8 right now. And then we're going to parameterize what I is doing. So we'll have int II, we'll have it start at 0. II is less than width, and then II, oops, What's that? Plus equals step. So the idea is that I is going to jump by steps each time. And the reason why we do that is we're going to have the other I actually start with II and then go to II plus step. So do you see what's happening here? Is that the idea is that II, the step I, so to speak, is going to jump by certain steps, and then the regular I is only going to work within that small step radius before it jumps to the next one. Okay? Should this code still, our regular I is still going to go through all the values. It's just going to go about it in a slightly different way, because it's going to go through first these I's internally before it increments again to do another set of I's. So if we go back here and we run it, do we still get the same answer? Yes. So we're still getting something correct. A very minor performance difference, and that's usually negligible. So we did it with I. We also should do it for J and K. Do you see what I'm doing with I? Yeah. So I'm going to do the same exact thing for J and then K. And I want to make sure I test it each time. All right, there we go. Hey, look, that was a performance decrease, so
Nice.
might not be doing anything. And then we'll do it one last time for K. And let's make sure we still get the same answer. Whoops, we probably should put our curly bracket. Ouch! Oh, that hurt. Okay. Wow, that was a significant performance difference. Well, anyways. All right, so we have that. We're getting the same answers. Let's go ahead and look at the 9. Let's see how much that takes under our new system. So we've added that blocking where we're only going to work within certain blocks before we move on. And we're going to see if that actually gives us a performance boost. Well, with 9.164 seconds, let me see, how does that compare with the other one?
Better.
Okay, that's definitely better. Okay. Well, let's see if that continues out to 10. Are you following me so far?
Yeah.
Okay, good. Sometimes I go into autopilot and then I'm just... .167.
Wow, that was 14.4, wasn't it?
1.67 as opposed to what?
14.
Think about this for a moment. Is the computer doing more work? Are there more additions happening?
It is, isn't it?
Yeah, it's doing more additions, it's doing more comparisons, yet it has nearly a whole order of magnitude speed up. Actually, if you carry this out, it's going to be even more, closer to probably 30 times once you get to really big situations. The point of this is to show you that when you work, if you work with the cache, you will get a very significant performance improvement. There's also one other very, I think, insightful piece of information. If you were to write matrix multiplication, which of these two would you write? If you were to just write it for work?
The first one.
The first one. What does that imply about most of your code?
Inefficient.
It's great.
Right. It's not that great. Well, maybe.
Well, it's not being paid for.
This implies most of the code that you write is not efficient or anywhere near perfectly optimized. Now, that doesn't necessarily mean that it's bad code, because it may be fast enough. But for the most part, you can get significant performance gains if you do at least a little bit of work in order to do the matrix multiplication. Okay. Yes?
How did you come up with your value for step there? I mean, that was just...
Really, this was actually a pretty good guess. I've done this a couple times, and I forget if it's 3 or 4 is the best. Let's do it with 4. 4 looks like it takes a little longer. I bet you 5 is going to really slow down. because 5 is how big those blocks are, and once those blocks get too big, they don't fit in the cache anymore. So you don't want your step size to be too big. And I
just wondered if you knew what the size of the cache was.
Yeah, you could sit down and calculate it. I haven't done it. Yeah, if you do it with 2, you go too small, it doesn't help either. You got to find the exact number. And actually, it's probably somewhere between, because I'm using order of magnitude 4, 8, 16, 32. It's probably somewhere in between. And you could play with this for a long time and figure it out. And in actuality, one thing I want to show you, I got 5 minutes. This is kind of an experiment because I just got this installed. I'm going to see if I can get it working. Let's see. I got it just installed, but I haven't been able to fully compile it. Let's see, Atlas MM. So what I'm doing here, oops.
That's some nerdy stuff.
It is some very nerdy stuff. What was I doing? Oh, Vim, this guy, go down to the bottom. So Atlas is a project that tries to automatically guess your cache sizes, how many bus references you can put out in the cache, and a bunch of other characteristics of your, whoops, I'll quit that, of your computer. And the point of that is to try and come up with the most optimal implementation of basic scientific, excuse me, basic scientific computations. So this one's CBLAS DGEM, which is basically doing the double matrix multiply. And if I recall correctly, in for this case is just width. And if you look it all up, there's a lot of parameters you can send it. I'm trying to stick with the default just for the sake of time. And if this works out the first time, that'll be great.
100 for everyone.
I love how quickly you jump to that. It makes me happy, I think. So if I compile, it's not going to work because we don't have CBLAS, so we need to...
See, I made a good bet. I knew it wouldn't work.
You knew it wouldn't work the first time? I think we got to do, what is it, like Atlas... no, it's not Atlas. It's lib Atlas include. All right, and then we got to. And how do we install the shared library? Thanks. I think I did a makefile here. Oh, you just include the shared library. Okay, great.
I was close.
I mean, what else would you do, right? Lib Atlas. Is it lib? There we go. Perfect. Same answers, and with lib Atlas, it took 0.1 second. That is opposed to our 1.6, and of course our naive, which is 14.05.
I think they're better than me.
Yes. Point 0.11 from 14.
They must be doing row reduction.
They're doing a lot.
They're cheating the matrices.
They're cheating the matrices.
And
But it gave the same answers. It's doing the same computations for matrix multiply. It's just doing them in a way such that the cache never gets full. Or I'm sorry, it makes it so that you're always doing cache hits. You're always utilizing the cache. You're not waiting on memory, or you're waiting on memory as few times as possible.
so, you compiled it using that.
So what I did is they have a shared object that has their version of matrix multiply.
Oh,
So
okay.
I just called it
Okay.
and then stuck it in during compilation.
I should have just done that for the assignment.
Yeah, what else would you do?
Genius.
All right. So hopefully I've given you, at least from a performance perspective, why understanding how cache systems work is very important. Is it blatantly obvious now? I hope so. Yeah, because this is that's a factor of 100 speed up, isn't it? It's 100 times faster?
100's not a big number.
Yeah, 100 times back, not 100%. So that would be, if it was percentage, it would be what, 10,000? 10,000% faster, more than. So, any questions? Thanks, Matt.
Pork chops.
It's not.
Guess none. All right. Well, thank you, Bart. There is no class next week, by the way.
Okay.
It's spring break.
Oh. yeah.
So if you come here, you'll be by
Oh, I
yourself.
missed it when I got here. Nobody was here.
No, it's next week. So no new material. You'll have your midterm. Yep.